Well, welcome everybody, and thank you for being here. So today we'll talk about electrochemical energy storage for underwater applications. So it's a sub-project number 9. All right. So first, a little bit of context. So the overall goal of this project is to increase the endurance and the performance of AUVs in terms of energy and power. So in order to do that, we are investigating the use of hybrid fuel cell and battery systems to power the AUVs. And so we are looking at clever ways to store hydrogen and oxygen as well. So I'm kind of working at 2 different levels. So one level is system design and modeling. So how do we find the best combination of fuel cell power and battery pack to meet the power demand at every time. And I'm also working on like small scale laboratory scale level where I try to find the optimum conditions of a fuel cell for such an underwater application. But yeah, maybe you don't remember, but why do we want to use fuel cell in AUVs? So this is a so-called Raguni plot, which is a favorite plot of all electrochemists. So here you can see the energy density in the x-axis and the power density of several electrochemical energy devices. And you can see here that the fuel cell system, they score very high in terms of energy density, meaning that we can store a lot of energy in a relatively compact system. And batteries, they score better in power density, but quite low in terms of energy density. So the idea of hybridization is actually to combine the energy density of fuel cells. We can pack a lot of energy in our system, so long missions. And we also combine that with some batteries so that we can reach high power peak demands. All right, so here are a couple of milestones for my project. So optimize the design of hybrid and battery systems for AUVs. Yeah, as I said as well, like find the optimum operation conditions for fuel cell in a closed environment. Then also like finding some strategies to share the power load between the fuel cell and the battery because we have 2 power sources now. And also think about thermal management and how it can affect the final design. But yeah, first thing first, yeah, for AUVs volume is pretty limited. And for an underwater applications, we need to store both hydrogen and oxygen to power the fuel cell. So the first step was to create like a sizing and optimization tool to find the optimum combination of fuel cell power and battery pack in order to meet the power demand. So I used real data from missions performed with Hugin. So, and I created like a tool that finds this optimum combination of fuel cell and battery and compares like several hydrogen and oxygen storage units. And then we also add the buoyancy compensation in order to reach neutral buoyancy. And that gives us like typically this kind of graph where we can see that for the same mission, here you can see 4 types of hybrid systems with liquid hydrogen and different types of hydrogen storage. So compressed at 200 bars, 700 bars, liquid hydrogen and metal hydride. And you can see the volume of the entire system and you can compare it with what it would have been with like a full secondary battery system or full primary battery system. And here we can see that when we choose wisely the hydrogen and oxygen storage units, we can compete and beat very easily the full battery system solution and always meet the power demand. And yeah, one of the major results from this study was this big energy density and specific energy plot, where we can see that when the emission increases, we reach kind of an asymptote in terms of energy density and specific energy for hybrid systems, depending on how we store hydrogen and oxygen. But we can see that those asymptotes are very high compared to the energy density of like secondary batteries or primary batteries. And yeah, and this study was, I wrote a full manuscript about it, and this article was accepted and is now published in the IEEE Journal of Oceanic Engineering. So you can find it. Then, as I said, the one important part was to find the optimum operation conditions for a fuel cell working in a closed environment. So, well, one thing is to save as much hydrogen as possible, and the idea is to make sure that all the hydrogen that goes in the fuel cell is forced to react. So one way is to use the fuel cell in so-called dead-end mode. So all the hydrogen is trapped inside. And we said that we have a fuel utilization of like 100%. However, it generates some accumulation of water and impurities within the cell, and that we can see like a drop of performance over time. So sometimes you need to open this purge valve here and let the hydrogen and the accumulated water leave the cell to restore its performance. So what I did is I made a nice setup in the lab where I put like a closed box with a fuel cell stack composed of 6 cells in series with hydrogen supply and oxygen supply. And I had like a purge valve for the fuel cell. I was working in dead-end mode. And I performed a design of experiment in order to find the optimum operation conditions for a fuel cell in such a condition. So the results were that the fuel cell should work at high relative humidity without or with very few forced convection and deliver a relatively low current. So in order to do that, we maximize the time between 2 purges. So we maximize the hydrogen utilization, and we also maximize the fuel cell performance over time. So yeah, that's kind of how it looks like in real life. So it's a bit messy, but it works. And yeah, I presented those results in the conference in December 2019. And then I wrote a paper about it that got accepted a couple of months ago, and it's now available in the International Journal of Hydrogen Energy. So here you can see like the different components of the fuel cell stack, different sensors, some valves, and yeah, everything was controlled with a microcontroller. All right. Now I want to go further on that study, and my idea is to try a new way of hydrogen, a new way to manage the hydrogen in the fuel cell. So the idea is to reverse the hydrogen flow after each purge. So in order to do that, I added a couple of freeway valves in my setup. And I also want to study the behavior of each cell within the stack. So it's more compares the degradation of each individual cell and run some electrochemical tests. So, well, the setup is now adjusted and is working well, and I'm performing these experiments nowadays. So the idea is to find an even more efficient hydrogen management strategy within the stack. All right, and now let's jump to another milestone, which is find a good ways to share the power load between the fuel cell and the battery. And yeah, this is a collaboration with Clemens and Chiche. But basically the question is, okay, we have 2 energy and power sources. So how do we share the load and manage the energy? So that's a graph from Clemens actually that I stole. But this is to show you the general idea. So we have power profiles from real missions, and we can model both the fuel cell and the battery pack. And the idea is to implement different types of energy management strategies to compare them and to see, in order to save as much energy as possible and to meet the power demand at any time. So yeah, it's a work ongoing, and yeah, we are modeling different components, and we want to size it so it's equivalent to a LOLO-like system. Yeah, as I said, we want to compare several strategies. We want to implement them on long missions. And yeah, we want to, of course, like compare the degradation of the different strategies on the fuel cell and the battery, and ensure their AUV reliability. So this is some kind of example of typical results we get from the previous study. So on the blue curve, you can see the power demand. In orange or reddish, you can see the power of the fuel cell during the mission, and in yellow, you can see the power of the battery. And here below, you can see the evolution of the battery state of charge during the mission. And yeah, the idea is to compare similar graphs for different EMS, so energy management strategies, and yeah, see how much hydrogen we consume, how much oxygen we consume, and see if we go to very low state of charge, which can mean that maybe we can have issues if we have upcoming obstacles, for example. So yeah, some results were presented at the AUV conference in 2020 by Clemens, and yeah, we are working on extending this study and making better model basically nowadays. And yeah, that knowledge jump as a milestone. So kind of the first step was to show that from a volume perspective, it was worthwhile to use fuel cell systems in AUVs, and we were like gaining a lot of energy. But yeah, if we look at it, we have a hydrogen storage unit, an oxygen storage unit, a fuel cell stack generating heat, battery pack that generates heat as well, a bunch of sensors. We have surrounding water around, and yeah, the idea is like how to include the heat properties of the reactant storage units in the design process, because now that we are sure that okay, it makes sense to use fuel cells, how do we include the heat properties of the different storage units in the design process? So in order to do that, I used my sizing tool to calculate the weight and volume for like of a energy storage system for a 50 hours mission. And I also calculated the total heat balance for each combination of hydrogen and oxygen storage units. So here you have a summary of, on this graph, on this figure, you have a summary of, like what the system looks like. And all the Q are where we have some heat happening. So we have the heat to release the hydrogen from the tank to heat it up to the fuel cell temperature, the heat generated by the fuel cell, same for oxygen, the heat generated by the battery pack, and the heat generated by the cooling of the water, for example. So the idea is to calculate the total heat balance for each combination. And then I performed the multi-criteria decision-making analysis to rank the different combinations. So to say it like in a simple way, using such a multi-criteria decision-making analysis is an objective way to compare pears and apples. So in our case, we have 4 criteria. So specific energy, energy density, the volumetric mass, and the total heat. So here we can see the weight of each criteria depending on which method we use. So we can see that it varies a bit. And here we see that the results. So we compare liquid, so we have liquid hydrogen and liquid oxygen being very well, scoring very well, because it's for one method, it's the first ranked method combination, and for one of the methods, the second best ranked method combination. And the combination of compressed hydrogen with liquid oxygen is also scoring very well. So yeah, it seems that metal hydride storage units, they're scoring quite bad. So here we can see like metal hydride with liquid oxygen or metal hydride with compressed oxygen are the 2 worst combination. So there is a high interest for liquid hydrogen and also for compressed hydrogen, if we see the results. So yeah, that's so we used objective criteria weighing in that case. So it must be seen as like a first step to see which combinations are more possible, and then we need to add more subjective criteria and more I would say expert knowledge point of view to really decide which storage we choose. And yeah, then I tried to extend a bit this analysis, seeing like how will the results of this multi-criteria decision analysis, decision-making analysis will vary with length of mission. And we can see that they are quite consistent with length of the mission for the 2 methods used. So we have some variation in the beginning, but we reach a plateau very fast. So it means that it's pretty consistent. And it also, how to say, correlates the results of the sizing tool, where we saw that after that the energy density and specific energy of the energy storage units, they were reaching an asymptote with time. So here we see that there is a plateau as well. So it correlates these results. So yeah, like future work. So more experiments in the closed box. We want to implement EMS, like energy management strategies, on longer pore profiles and improve the strategies on the model. Test more advanced energy management strategies maybe, and yeah, make sure that the heat calculations are correct and yeah, that it makes sense. Yeah, thank you for your attention. Please feel free to ask